Hello everyone. So in this session, we will look at the regular Falsi method, which is again another method to find the root of a continuous function um, in some interval a comma b, where f of a and f of b are of different signs. Okay, so generally this method is a little faster than the bisection method. So you'll get your result in fewer iterations. That's the uh, key reason that we would use the regular Falsi method over the bisection method. Okay, so basically we are going to discuss what is the next iterate in this um, method. Okay, so what is the how do I find those smaller and smaller intervals? Okay, so let's see here. Okay, I think we will use Cn instead of Xn. Okay, so in the bisection method, the uh, the nth iterate was essentially a plus b by 2. Okay, it was the midpoint of a and b. Here, it's not going to be the midpoint of a and b. It is going to be the point of intersection of the line segment that passes through a comma f of a and b comma f of b. Okay, that's the basic principle. So maybe I will draw out one graph and we'll see what is happening in that graph. So here you can see we would have a graph like this. Okay, at a, say it is negative, and at b it is positive. So this would be the point b comma f of b, and here you have your point a comma f of a. Okay, the line segment through a comma f of a and b comma f of b is this. So at the first stage, this would be your C1. Okay, so this would be my C1. Okay, and again using the similar principle as we have used in the bisection method. Okay, that is the intermediate value theorem. Since the value at C1 is negative, you can see from the graph that the value of C1 is negative. We would replace A by C1. Okay, we would replace A by C1. So in the next iteration, this will become A. Okay, now look at these 2 points. Okay, so this would be your C1 comma f of C1, or now in the new this things will be A comma f of A, and your b comma f of b remains the same. And then again we draw a line segment passing through, let us draw blue one this time, to this new iterate, to this new point and b comma f of b. Okay, so then this would be your new C2. This would be a C2, and again you can see that at C2 the value of f is negative. And in fact, very often in the regular Falsi method, as you can see, when the derivative does not change, generally we will be talking about differentiable functions. When the derivative doesn't change, you will generally notice that it will be just the value of a that keeps changing, or just the value of b that keeps changing. You will not get points in this graph. In fact, you will not get points at which f of c is going to be positive. It will never be able to go to the right hand side. That's the idea. Okay, so you will keep going closer and closer to the 0. In fact, you can intuitively believe that this is much faster than the bisection method. Okay, so let's see how we are going to get this. So what we want here is we want to find out what this value of f of c1. We are not going to be drawing the secant and computing it at every time, right? So let us find out what this value of Cn is. Okay, so let us calculate the value for xn. Okay, so to calculate the value for xn, we should first know what is the equation of the line passing through a comma f of a and b comma f of b. So the equation of the line would be, okay, passing through these 2 points, that is a comma f of a and b comma f of b, is going to be y minus f of a upon x minus a equals f of b minus f of a, yeah, divided by b minus a. Okay, now Cn is the point at which the value for y becomes 0. So therefore, what happens is, you can see here, this is the point at which the y coordinate is 0. So this will mean that we have minus f of a divided by Cn minus a equals f of b minus f of a divided by b minus a. Okay, so cross multiplying, what we get so we can, yeah, cross multiply and we get Cn minus a would be equal to minus f of a times b minus a divided by f of b minus f of a. Okay, and adding throughout by a, we will get Cn equals, that is a times f of b minus f of a minus f of a times b minus a upon f of b minus f of a. Okay, so see, here we have 2 terms that cancel out, that is this is a times f of a minus f of a, and here we will get f of a multiplied to this gives us plus a times f of a. So this will cancel out with this term, and then we are simply left with a times f of b. In the numerator we are left with a times f of b minus b times f of b. So what is the value for Cn? It is nothing but, Cn is nothing but a times f of b minus b times f of a divided by f of b minus f of a. Okay, so that's the value for Cn. So at every stage, this is how we find Cn, the new iterate. Okay, so let's solve one problem using the regular Falsi method. Okay, so the process will be exactly the same as you have followed in the bisection method. So the algorithm is compute first, of course. Here let me just for the sake of notation, let us use C in place of x, C1, okay, so we'll use C's in place of x, and so this algorithm again is used to find a root of a continuous function f in an interval a comma b where the product of f of a and f of b is negative, or in other words, one of f of a is positive and the other one is either f of a or f of a b is positive and the other one is negative. They are of different signs. So we want to find it correct up to m decimal places. So what we do is we simply repeat the iterations till the error becomes less than 10 raised to minus m plus 1. Okay, that's the basic principle. So let's look at how do we use the regular Falsi method to find a root of the function. Say f of x equals, in this case we are looking at x square e raised to x minus x cube minus 5 in the interval 1 comma 2. Okay, now if you plug these values here, what you will see is that the value at a or f at 1 is minus 3.282, and the value of b, of course I am rounding up at the third decimal place, and f at 2 is 16.556. Okay, this is what we can see. Okay, so how do I calculate this value of c? So c1 is nothing but a times f of b, that is, let us write it in this case. So this would be 1 times f of b is 16.556 minus b times f of a, which is 2 times minus 3.282 divided by f of b minus f of a, which is 16.556 minus 3.282. Okay, and what you will get when you compute this using your calculator and round up at the third decimal place, you will get 1.165. Okay, with that, now you compute the value of f of c. Okay, plug in the value here and compute what the value of c is. What is this error? In the start, it is okay to take this error. If you want, just don't compute the error at the first stage, that's also fine. I have simply taken it as b minus a. You can't really compute anything here. Okay, now the value of c is negative. So since the value of c is negative, you can see this one is the one which is negative and this one is positive. A and b are not negative and positive, but f of a is negative and f of b is positive.